Okay, let's get started with lesson 3, factors affecting the rate of a chemical reaction. The first factor we're going to look at is temperature. Now, there are two major ways in which temperature affects the rate of a chemical reaction. This is indicated in our first bulletin point. Number 1, at a higher temperature, there is an increase in collision frequency. This is due to a higher average kinetic energy that the molecules are going to have. But more importantly, the second factor here, there is an increase in the number of collisions involving particles with the necessary kinetic energy to overcome the activation barrier. So this statement indicates the two important factors that would generate an increase in the rate of the reaction due to an increase in temperature. All right. Now there's a lot there, so let's take a moment and summarize those 2 points and talk about them a little bit. Okay. So according to that statement, then, an increase in temperature should speed up the rate of the reaction, all right, with increasing temperatures. Okay, now what are the two factors? Number 1, right, an increase in temperature would result in an increase in the number of collisions. All right, why is that? Why is there an increase in the number of collisions? Now, this is probably common sense. So if you think about it, if your temperature goes up, you're adding more energy to these molecules. So therefore, they're going to have more freedom of movement, and their speed is going to increase. Well, if the particles are moving at a higher speed, then there's going to be a greater chance that they're going to collide with one another. And just that fact that they're going to increase in the number of collisions should increase the rate of the chemical reaction. However, point number 2 is more critical than point number 1, and you need to understand that. In fact, is on the AP and IB exam, they will want you to understand that the second point is more important than the first point. So what is the second point? Well, there should be essentially an increase in the number of particles with energy greater than the activation energy needed to start the reaction. All right. All right. In other words, we're going to increase the number of successful collisions. There's going to be, as you essentially increase the temperature, we have more molecules that are moving faster. They're colliding more often, but it also will increase the number of molecules that have energy that's above that activation barrier. And so therefore, there's going to be a greater number of successful collisions that will result, of course, in an increase in the rate of the chemical reaction. All right? So these are two very important points in how increasing the temperature speeds up the rate of a chemical reaction. All right, let's go back to our other 2 bulletin points here. The second one states that an increase in temperature then results in an increase in the number of successful collisions, and so an increase in the rate of the reaction, which we just said. And of course, the only way we can have more successful collisions in this case is that more molecules have energy higher than the activation barrier line. All right? And this is also an interesting idea, is that for many reactions, if you double, or many reactions, they're going to double their rates for every 10 degrees increase in the temperature. All right, so let's use a Maxwell-Boltzmann's distribution curve to explain our understanding of how temperature affects the rate of a chemical reaction. So you should be very familiar with these. So let's do this. All right, there's a Maxwell-Boltzmann's distribution curve. We're going to say at a high temperature for a particular system or chemical reaction. And then we're going to compare that to one at a lower temperature, or sorry, this is going to be the lower temperature at. Just kidding. Let's use this as the low temperature. All right. Now we're going to increase the temperature. We're going to get something like this. So we're going to say this is the higher temperature. Okay? Now, down here, is going to be our EA. Okay, that's the activation energy barrier. All right, so at the lower temperature, according to this graph, there's going to be a small fraction underneath this curve, a small fraction of molecules with enough kinetic energy that when they collide are going to form successful collisions and be able to react. Okay, remember that molecules down in this area just simply do not have enough energy that when they collide will actually chemically react. Molecules have to have energy at or above the activation barrier in order for them to chemically react, which we learned in lesson 2. All right, but what happens at a higher temperature? Well, at a higher temperature, there's going to be a higher fraction of molecules with kinetic energy that's greater than the barrier, activation barrier, in order to chemically react. And so again, the Maxwell-Boltzmann's distribution curve explains the second factor of increasing the temperature, which again states that as the temperature increases, there's going to be a greater percentage or a greater number of molecules that have energies, kinetic energies, above or at the activation barrier. And so there will be more molecules that are there in order to react. All right? So again, these molecules can react. These molecules can not react. Right? So by increasing that temperature, it just gives us more molecules that are able to react due to their kinetic energies. All right, so hopefully that makes sense. Think about this, review your notes, and give yourself some time to think about these two factors and how temperature influences the rate of the reaction. And make sure that you can be able to describe those factors using a Maxwell-Boltzmann's distribution curve. All right, now we're going to go to our second factor, which is concentration. Now, concentration is easier to understand than temperature. Essentially, increasing the concentration of the reactants increases the rate of the chemical reaction. Why does this occur? Well, as the concentration increases, there's going to be a frequency or an increase in the frequency of particle collisions. All right? So therefore, this is going to result in an increase in the number of successful collisions. We can illustrate this in this diagram below. All right? So let's say that we have some particles at low concentration, and they have kinetic energy, so they're moving. That's represented by the arrows as the directionality these particles are moving at low concentration. Now let's look at higher concentration. At higher concentration, the number of molecules is going to increase greatly. So what are the chances that these molecules are going to collide with one another? They're going to be much higher frequency. So let's just draw this out. Here's another collision. All right, and then down here we'll have another collision. All right. The point is that as the concentration increases, there should be more collisions, or the frequency of collisions should go up, so therefore the rate of the reaction should occur at faster at higher concentrations than at lower concentrations. Think of it this analogy, all right? Think of the fact that during passing periods, there seems to be a greater number of students than when there's not a passing period. And so what is the chances that you're going to collide with another student while you're moving from one class to another? The chances are going to go up quite a bit. There's going to be a greater frequency of collision the higher the concentration of students. Whereas when students are moving through the halls, when passing periods are not occurring, there's going to be a very unlikely chance you're going to collide with another student because the frequency of students go down, or the concentration of students go down. All right? So that's pretty easy to understand. Bottom line is you increase the concentration, you increase the frequency of collisions, therefore you increase the rate of the chemical reaction. All right, what about pressure? This is our third idea here. Well, for reactions involving gases, and this only deals with gases, so for reactions involving gases, increasing the pressure increases the rate of a reaction. Why is this the case? Well, the increase in pressure will decrease the volume. All right, that's Boyle's law of the gas, resulting in an increase in the concentration. All right, so therefore, since we're going to increase the concentration of the gas particles, there should be an increase in frequency of collision. All right, so let's illustrate this idea. So if we have a container here, and it's got gas particles moving around, all right, and it has let's say, a low pressure, so the pressure is low, but if we increase the pressure of the container, all right, so that means that the volume goes down. Actually, let's make a smaller volume here. So if we increase the pressure on the container, the volume goes down. So the pressure high, remember Boyle's law, pressure goes up, volume goes down, all right? But with that, it creates particles, gas particles, that are in a smaller volume. Well, if the volume goes down, the concentration goes up, all right, for these gas particles. And so here we just apply the same ideas of an increased concentration. We increase the concentration of these gas particles, and increases the frequency of collisions. Therefore, the rate of the reaction should go up, right? So there's pressure for us. All right, what about particle size? how does the size of particles affect the rate of a reaction? Well, here we see that decreasing, when we decrease the particle size, we're actually going to increase the rate of a reaction. Subdividing a large particle into smaller parts increases the total surface area. Therefore, it allows more contact and a higher probability that collisions are going to occur with the reactants. Okay, so here we have an illustrated diagram. So here we have a particle here, and we're going to take the same particle and we're going to break it down into smaller chunks. Now, when we do that, we break it down into smaller parts, right? We're going to increase the surface area. For these particles. And in a bigger surface area, or more exposure of the surface to reactants, there should be more collisions. So an increase in surface area results in an increase in collisions, therefore an increase in the rate of the reaction. An analogy, think of like a sugar cube. If you have a big sugar cube versus taking that same sugar cube and breaking it up into smaller pieces, all right, the smaller pieces have more surface area, so that sugar should actually react much faster at those smaller pieces than at the larger chunk, all right? So that's how particle size affects the rate of the reaction. All right, the last one we're going to look at is catalysts, right? This is a biggie, very important to understand how a catalyst affects the rate of a chemical reaction. All right, so let's look at these ideas. So catalysts increase the rate of a reaction by lowering the activation energy of the reaction or reaction steps without itself, and this is important, without itself being consumed during the reaction. All right, so what we're saying is that when we add a catalyst to a reaction, it lowers the activation barrier. So therefore, there's going to be more particles with enough energy to be able to react. More there. However, a catalyst is a chemical, and it is not consumed during the reaction. Right? Now, most catalysts work by providing an alternate route for the reaction, which has a lower activation energy barrier. All right? So let's put these points into an energy diagram or a graph, all right, and take a look at this. All right, so let's say we have a chemical reaction that's going to occur, and we have something like this. Okay, so we have the reactants, we have our products, all right. The energy difference here is delta H, which is exothermic. And you should know that by now. You also should know that the energy here that comes to this transition state right? That energy is the activation energy needed for the chemical reaction to go. All right? So what would happen if I add a catalyst to this reaction? Well, it's going to alter our graph here for certain. Oops. I just erased. Okay, we got to go back and redo this now. All right, so again, draw this. Our reactants, our products, transition state. This is delta H, which is negative exothermic. This energy barrier is the energy of activation. It's positive. We need energy in order to initiate the reaction to get that transition state. All right, now what we're going to do is we're going to add a catalyst. So what a catalyst is going to do is, by definition, lower the activation barrier. All right, it doesn't change delta H. All right, it does not affect the thermodynamics here. What it does do is it creates a smaller activation barrier. All right, so this right here represents the catalyst or catalyzed reaction, and the one in red represents the uncatalyzed reaction. All right, so hopefully you see from this graph that all a catalyst is going to do is lower the activation barrier. So we don't need as much energy in order to start or initiate the reaction to create the transition state. In fact is, we are going to form a brand new transition state. A transition state that is more stable, that requires less energy to form when we add the catalyst. All right, so these two transition states are not the same. They're different from one another. Because as was stated before, usually a catalyst is going to find an alternative pathway that produces a transition state that's more stable than the normal pathway. And that way it lowers the activation energy barrier. Okay? So the lower activation energy means that a greater number of particles will possess the required minimal energy, and a greater number of collisions will be successful, resulting in a chemical reaction. All right, to finish up this idea of how a catalyst affects the rate of a reaction, we're going to do another Maxwell-Boltzmann's distribution curve. All right, so essentially, let's take a look here, curve here, like so. All right, now under normal circumstances, the activation barrier line is going to be right here. All right, and so this fraction of molecules above that line has enough energy to react. Okay, that's without the catalyst. Okay, now when we add a catalyst, though, what is it going to do is it's going to lower that barrier. Okay, and so now what's going to happen is with the catalyst, we're going to have a greater number of particles all the way through, a greater number of particles that have energy enough to react. Okay? That's with a catalyst. So all we're doing is moving that barrier line. Now compare this to temperature. Remember in temperature when we wrote out or illustrated this Maxwell-Boltzmann distribution curve, we did not move the activation barrier line at all. Okay? All we did is when we increased the temperature, we increased the number of molecules that had enough energy to overcome that activation barrier. Okay? That's what temperature does. Temperature is not a catalyst. All right? In fact, is increasing the temperature does not increase the rate of reaction like a catalyst does. All right? They're two different complete things. Besides, increasing the temperature deals with energy, where a catalyst is actually a chemical. It's actually a chemical added to the reaction mixture that is going to lower the activation barrier. All right? So I need you to really understand how catalysts work and compare and contrast the difference between how a catalyst works and how increasing the temperature works on the rate of the reaction. All right? In fact is, let's finish up. Let's draw one more diagram with showing an increase in temperature. Okay, so here's one. Okay, we're going to increase the temperature now. All right, so by increasing the temperature, we're not changing that activation line. It's staying right where it is. But now we have more molecules, or a higher percentage of molecules with enough energy that will be able to react when we increase the temperature. All right, hopefully this makes sense. All right, make sure you study this. This is all for this lesson. I know there's a lot to think about here. Go back and re-look at this lesson or lecture video if you need to. Study your notes and prepare for the quiz. And that is all for right now.